Okay, so welcome back, and today we're going to talk about arc length as it regards to parametric curves. Okay, so now, just like before when we were dealing with regular functions, we had a formula for arc length, right, to find the arc length of a curve, right? And we started with these secant lines, these line segments. So we're going to do the same thing. So let's set it up. So I've got this curve, and I've got these points along the curve, right, where we're going to find our line segments, and we're going to find the distance, right, the length of each line segment, which is by finding the distance between each point, we find the length of the line segment. And so what we're going to do is, if we add up all those line segments, we'll get an approximation for the length of the curve, okay? Just like before. But now we're doing it with parametric equations, and we're looking at a parametric curve. Okay, so again, we're taking our x and y coordinates, right? Those are functions of t, so they're parametric equations, and we're taking t over the interval from a to b. And just like before with area, we're subdividing the interval into regular subintervals with endpoints at t0, t1, all the way to t sub n. Okay, and then the length, of course, is delta t, which is given by our formula that we use, b minus a over n. Okay, so we know the distance is delta t. Okay, now what's the distance formula, right? So all we're going to do is we're going to find the distance between 2 points. So if we take from t0 to t1, right, on the subinterval, then we know the distance 1, if you will, is equal to the square root of what? Well, distance in the x's, so it's going to be x of t1 minus x of t sub 2, quantity squared, right? And then we want to add that to the difference in the y's, which is going to be y of t sub 1 minus y of t sub 0. Oh, did I say? No. This should be 0, not 2. 0. T sub 1 minus t sub 0, and then y of t sub 1 minus y of t sub 0, quantity squared. Okay, so now that would be like the first line segment from t0 to t1, right? So from t0 to t1, this would be the distance of the line segment, the length of the line segment. Then we're going to do d2, right? So d2 would be then the next line segment. And so in this case, it would be the same thing, but it's going to go from x of t1, or excuse me, x of t 2 to x of t1. So minus x of t sub 1, oops, squared. Squared, okay, plus y of t2 minus y of t1, quantity squared. Okay, and so that gives us the distance of the second line segment. And we keep doing this, right, over and over and over again until we get to the end, right? So we take all of these line segments, right, all of these distances, if you will, these lengths, and we add them up. Okay, so if I wanted an estimate of S, right, the arc length, S. So we keep doing this till d sub n, right, so this would be, x of t sub n minus x of t sub n minus 1 squared, quantity squared, plus, and then we do the same thing, y of t sub n minus y of t sub n minus 1 quantity squared. Okay, so we take all of these and we add them up, right? So what do we get? Okay, we get an approximation for S, right? So we get S equals approximately the summation, right? So S represents the length, the arc length is approximated by the summation of these distances. Okay? So for I equals 1 to n of d sub I. Okay. Okay, so now, so far so good. Okay, so now, again, I'm going to erase this, and now what I'm going to do is I'm going to put this together as a formula. Okay, so let's erase this. So now, so the arc length, again, we're going to use S, right, is the exact arc length. And we're going to use S sub I, right? Instead of D sub I, we'll use S sub I. So S is the exact arc length, is approximately equal to S sub n, S sub n, not S sub I. S sub n, right? And S sub n is going to equal what? That's going to be the sum of all of our distances that we just derived. So that's going to be the sum of I equals 1 to n, okay, of what? Of our distances, right? And so this is going to be equal to x sub t sub I minus x of, so x of t sub I minus x of t sub I minus 1 quantity squared plus y of t sub I minus y of t sub I minus 1 quantity squared. So that's our summation. Okay? Now, we're assuming, right, so again, if we assume that x sub t and y sub t are differentiable, okay? So if we assume that x of t and y of t, x of t and y of t are differentiable, then we can use the mean value theorem. Well, why would the mean value theorem be important? Well, because if they're differentiable, then the mean value theorem tells us that there has to exist a point on the interval, or in this case, each subinterval. There has to exist a point on each subinterval where the slope of the tangent line that intersects that point is the same as the slope of the line segment connecting the 2 points. Okay? So, for example, I have this line segment, right? So this line segment represents the approximate arc length that we're using. So if y and x are differentiable functions of t, then that means we can apply the mean value theorem. And so what does the mean value theorem say? It says if we have a closed interval on a to b, or in this case from t sub I minus 1 to t sub I, okay, then there must exist a point somewhere on the open interval from t sub I minus 1 to t sub I such that the slope of the tangent line at that point is the same as the slope of the secant line. So in other words, this slope here, right, which is what? The slope of the line segment, right, is given by what? It's f of, in general, remember, in general, it's f of b minus f of a over b minus a, right? That's the slope of the secant line. So the mean value theorem says there must be a point c, some c value here in the interval, such that the slope of the tangent line at that point, f of c, right, must be the same as the slope of the secant line. So this is the average rate of change for this. This is the slope of the secant line, right? The line segment is equal to f prime of c, right? So that's the mean value theorem. So now if I multiply both sides by b minus a, I get this, right? So this means that what I can do is I can use the mean value theorem in here, okay? And I can start simplifying things using this, okay? So, and you're thinking, well, how do I do that? Well, what do I have? I have this minus this, and I have this minus this. Well, aren't these two functions of t, and this is a function of t? I can use this, okay? So, what am I going to use? Well, that means that there must be some point on each subinterval. Let's call one t sub I star, right? There must be a point t sub I star and t sub I double star on each subinterval such that what? X of t sub I minus x of t sub I minus 1 is equal to, now here's where the mean value theorem comes in, x prime, right? X prime of what? T sub I star, let's say. T sub I star times what? B minus A, which is just going to be T sub I, minus T sub I minus 1. Okay, so that's for the x's, right? Now the same thing can be said for the y's. So that means there's also a t sub I double star such that y of t sub I minus y of t sub I minus 1 is equal to y prime of t sub I double star times t sub I minus t sub I minus 1. Okay, so far so good, I hope. Okay, so now what I'm going to do is I'm going to replace both of these in here with these. Okay? And so now, what is this? These two is just delta t, right? So I'm just going to basically replace these with delta t. So what do I get? I get x prime of t sub I star times delta x, and the bottom one becomes y prime of t sub I double star times, not delta x, I'm sorry, delta t. Delta t, okay? And so now what I'm going to do is I'm going to replace both of these under the squares with that. Okay, so what does that do? So how does that affect my calculation? Okay, so again, this is just a note, right? So again, just to recap, using the fact that we're assuming that x of t and y of t are differentiable. If that's the case, then we know there has to be some point on the interval. Some value between, for each one of these subintervals, there has to be a point such that, by the mean value theorem, right? Again, we're using the mean value theorem. There has to be a point on each subinterval such that the slope of the tangent line at that point is the same as the slope of the line segment connecting the two endpoints. And so now we're using the mean value theorem, which basically says this must be true. And we're applying it to 2 points, one point on each, such that this for each one, right? We have to do it for separate for each function. Okay? And so we get these two equalities. Okay? And so now I'm going to substitute. Okay? So, what does that mean? It means that this okay? This is going to end up equaling what? It's going to equal the sum as I equals 1 to n of what? Well, now this is going to become this. So this is going to become x prime of t sub I star times delta x, right? Quantity squared right? And then, of course, this is going to be plus, and then this is going to be y prime of t sub I double star times I keep saying delta x, not delta x, delta t. Okay, that's going to be squared. Okay, so now this is what I use this for, to do the substitution. Okay, now you'll see why I did that. Okay, so now we're going to simplify this. Okay, so I'm going to distribute. And so what happens to this? This is going to become I equals 1 to n, the square root, and this is going to become x prime t sub I star squared times delta t squared plus y prime of t sub I double star squared times delta t squared. Okay, so now here, what happens to this? Well, this is just going to be the derivative of x of t, right? This is going to be the derivative of y of t squared. Both of these are squared. Then we have delta t squared. Well, now what we're going to do is we're going to factor out the delta t squared, right? Because it's under the radical, we can factor this out, and what do we get? We get the sum as I equals 1 to n of the square root. And what do we get? We get x prime of t sub I star squared plus y prime of t sub I double star quantity squared, and then we pull this out and we just get a delta x. Now, and the fact that this can be pulled out, since there's no i's, this is just going to be the same, so this can be pulled out of the entire sum. Okay? So this is the Riemann sum that approximates the arc length over a partition of the interval from a to b. Okay, now if we further assume that the derivatives are continuous, we haven't talked about that, but if we further assume that the derivatives are continuous and let the number of points in the partition increase without bound, right? So we're going to take the limit of the partition. So as n approaches infinity, we get the exact arc length. So now what we're going to do is we're going to take the limit, right? So now we're going to take the limit of this. So what is it? What happens there? Okay, so let's start up here. I'm going to erase this here. Okay? Because it served its purpose. And I'm going to start erasing some more of this, but let me rewrite this. Okay, so what do we have so far? We found that S, right, is approximately equal to S sub n, which is equal to the summation as I equals 1 to n of this. So we get x prime of t sub I star, quantity squared, plus the quantity of y prime of t sub I double star, quantity squared, times, keeps putting delta x here, it's delta t. Delta t, not delta x. Okay, now, that's what we have, right? But let's take the limit, because the limit is the exact. So now what we're going to do is we're going to take s is equal to the limit as n approaches infinity of s sub n, which means this is the limit as n approaches infinity of this entire thing. Right? I don't want to rewrite the whole thing. So now, what happens when we take the limit? So now, again, the intervals are getting smaller and smaller and smaller and smaller. They're going to a width of 0, right? So eventually this delta, this t sub I star and this t sub I double star are both just going to be t. Okay? This is going to become dt, and this is going to become our integral symbol. Okay? So this is going to give us the integral from a to b of what? It's going to be the square root of x sub I, x of t, x prime of t, quantity squared, plus y prime of t, quantity squared dt. And that is our final result of everything. Okay, so that is the integral that will give us the arc length when we're given parametric equations. We're given a parametric curve, so we're given parametric equations over an interval of t. This is the integral that we will use to find the arc length of such a curve. And next will be the theorem. Okay, let's see here. Is there anything else I want to say before I let you guys go? Okay, I guess the only thing is to reiterate is these 2 points, even though we're not assuming that these 2 points are the same, right? That's why I put star and double star, because there's no reason to believe that those 2 points using the mean value theorem should be the same. But when you take the limit, these 2 points are going to converge to the same point. Okay, so that's why I just put t in for both of those. But again, that's just going back to similar arguments that we've made in past videos. Okay, other than that, I'll see you next time and we'll introduce the theorem.